A tunnel diode is a p-n junctio that exhibits negative resistance between two values of forward voltage, that is, between peak point voltage and valley point voltage. Theory: the tunnel diode is basically a p-n junction with heavy doping of p-type and n-type semiconductor materials. In fact, a tunnel diode is doped approximately 1,000 times as heavily as a conventional diode. This heavy doping results in a large number of majority carriers. Because of the large number of carriers, most are not used during the initial recombination that produces the depletion layer. As a result, the depletion layer is very narrow. In comparison with conventional diode, the depletion layer of a tunnel diode is 100 times narrower. The operation of a tunnel diode depends upon the tunneling effect and hence the name. Tunneling effect: the heavy doping provides a large number of majority carriers. Because of the large number of carriers, there is much drift activity in p and n sections. This causes many valence electrons to have their energy levels raised closer to the conduction region. Therefore, it takes only a very small applied forward voltage to cause conduction. The movement of valence electrons from the valence energy band to the conduction band with little or no applied forward voltage is called tunneling. Valence electrons seem to tunnel through the forbidden energy band. VI characteristics. Figure shows the VI characteristic of a typical tunnel diode. 1. As the forward voltage across the tunnel diode is increased from 0, electrons from the N region tunnel through the potential barrier to the P region. As the forward voltage increases, the diode current also increases until the peak point P is reached. The diode current has now reached peak current IP equals 2.2 mA at about peak point voltage Vp equals 0.07 volts. Until now the diode has exhibited positive resistance. 2. As the voltage is increased beyond Vp, the tunneling action starts decreasing and the diode current decreases as the forward voltage is increased until valley point V is reached at valley point voltage Vv equals 0.7 volts. In the region between peak point and valley point, that is, between points P and V, the diode exhibits negative resistance, that is, as the forward bias is increased, the current decreases. This suggests that tunnel diode, when operated in the negative resistance region, can be used as an oscillator or a switch. Note: if current flowing through a circuit or device increases as the applied voltage is increased, we say that the circuit or device has positive resistance. 3. When forward bias is increased beyond valley point voltage Vv equal to 0.7 volts, the tunnel diode behaves as a normal diode. In other words, from point V onwards, the diode current increases with the increase in forward voltage, that is, the diode exhibits positive resistance once again. Figure 2 shows the symbol of tunnel diode. It may be noted that a tunnel diode has a high reverse current, but operation under this condition is not generally used. Applications. One application is tunnel diode oscillators. A tunnel diode is always operated in the negative resistance region. When operated in this region, it works very well in an oscillator. Figure 1 shows a parallel resonant circuit. Note that Rp is the parallel equivalent of the series winding resistance of the coil. When the tank circuit is set into oscillations by applying voltage as shown in Figure 2, damped oscillations are produced. It is because energy is lost in the resistance Rp of the tank circuit. And biased at the center of the negative resistance portion of its characteristic as shown in below figure, undamped oscillations are produced at the output. It is because the negative resistance characteristic of the tunnel diode counteracts the positive resistance characteristic of the tank circuit. The circuit shown in below figure is called tunnel diode oscillator or negative resistance oscillator. While the circuit works very well at extreme high frequencies, upper megahertz range, it cannot be used efficiently at low frequencies. Low-frequency oscillators generally use transistors.